Hey everybody, we have a very believable looking result. Let's go ahead and just show that it holds for this one special case. Let's pick n equals 5, n's a natural number. And let's go ahead and make it simple. Let's pick k equals 1. And it's important for k to be a non-negative integer here. All right, so we'll pick k equals 1. Now notice what happens here. This would be 4. K is 1. This would be 4 cubed plus 1 equals 65. Okay, which is of course divisible by 5. This is equal to what, 13 times 5? Which is what mod. You could think of 5 as being congruent to 0. In fact, that's normal interpretation. So 5 is the same thing as 0 mod n. So, I mean, mod 5. And so, anyway, this is an example that makes you tend to believe this result. Now, also, the binomial theorem is, it's a very easy proof if you're familiar with it. That's because minus 1, the last term in the binomial expansion would be minus 1 raised to an odd number. And the odd part is important, okay? So you see what happens here, then you have the plus 1. And again, y'all, all I'm doing is applying the 2k plus 1 to this very last term, and the minus sign sticks around, right? And so this is equal to 0. But again, if you're familiar with the binomial expansion, all the other terms would have multiples of n. So would be multiples of n. All the other terms, you know, would be n raised to the 2k plus 1 is obviously by definition a multiple of n. In the binomial coefficients are just integers. All the other terms, you would have 1 and then n raised to power. So everything left would be would resolve to a multiple of n. And so the binomial proof is easy only if you know what it is. And it's a very common result in mathematics. But I'm interested in a way that involves modular arithmetic, okay? And so I'm going to take a look at n minus 1 squared, which kind of comes up here if you take a look at, if you remind yourself of properties of exponents. Now, notice what happens here when you expand this out. You get n as a multiple of n, namely n minus 2 times n, okay? But this right here, this statement right here is really the very same thing as saying that n minus 1 squared is congruent to 1 mod n. Now, oh yeah, down here I wrote it a little more explicitly. You could take n minus 2 to be m if you like to minimize the number of symbols in your face. But this statement right here and this statement right here are absolutely equivalent, okay? It means the very same thing, okay? In other words, there's 2 or 3 ways they look at congruence in number theory books. This is one way, this is another way. There's even another where you just think about remainders, you know. But in any event, we do know that n minus 1 squared is congruent to 1 mod n for all n. Okay, now the rest of this is just algebraic manipulation. This is the expression we were interested in, so we can rewrite it like this, laws of exponents, right? There's an understood exponent of 1 right there. That's where you get the 2k plus 1 right here. Okay, now, again, properties of exponents, but we just showed that n minus 1 squared is congruent to 1. So this would be, now we can switch to the congruent symbol. It's a little bit of a subtle switch, but from the equality, we go to congruence here, and we get 1 to the k times n minus 1 plus 1. Folks, but let's see, that's just equal to n, right? I'm sorry, let me write the plus 1 right here. Plus 1. Every time I talk, I forget to write stuff down. But this is just equal to n, right? Which is certainly congruent to 0 mod n. Okay, so y'all, we've proved what we set out to prove. It is congruent to 0 mod n, and that takes care of the proof, and we did it without using the binomial theorem. So that's the only thing about this. It's a fairly easy result, but a lot of people would just say, oh, binomial theorem done. But again, noticing that the order of n minus 1 is actually 1 n-1 squared. That has an n-1 has an order of 2 in number theory terms, and that turned out to be useful right here. So anyway, let's put QED right here.